I'm Manori Dissanayake. I'm a PhD candidate from Griffith University, Australia. Today, my presentation will focus on emission calculation methods of aircraft, a systematic literature review. With me are Professor Tim Riley, Dr. Bojana Spasojevic, Dr. Savindi Caldera. Aircraft influence the environment in various ways. Aircraft operations below 3,000 feet cause degradation of air quality by emitting gaseous pollutants, nitrogen oxides, carbon monoxides, sulfur dioxides, and hydrocarbons. However, 90% of aircraft emissions influence climate change, while 10% influence the local air quality. Even though only 10% of aircraft emissions influence the local air quality, it directly impacts all living beings. This is an issue for the aviation industry because poor air quality is an environmental cost for airports and airlines and gives them a negative image. Therefore, this research directly examines the impact of aircraft on air quality. The research problem was constructed considering two main areas. Firstly, around 70% of aircraft emissions include carbon dioxide causing climate change. Therefore, climate change gets priority over local air quality. However, in addition to climate change, it is imperative that the aviation industry focus on air quality. This diagram presents the phases of a flight. The landing takeoff cycle or LTO cycle consists of phases below 3,000 feet. Climb, cruise, descent cycle or CCD cycle consists of phases of flight above 3,000 feet. Most studies have measured aggregate emission of both LTO and CCD cycles. However, the exact amount of emissions during different flight phases have not been clearly identified. These are the steps that we followed when conducting our systematic literature review. After finalizing the research question, research scope, and keywords, a sample of the relevant literature was retrieved from the selected databases. This literature was screened, the findings were synthesized, and the final step was to evaluate and present the results. Two main research questions were addressed through this systematic literature review. What existing measures and research gaps in the literature concerned the impacts of aircraft on air quality, and what emission calculation methods can be applied to assess the air quality below 3,000 feet. The emission calculation methods that were used in previous studies needed to be identified. Therefore, keywords were searched within 3 scholarly databases. Peer-reviewed journal articles published from 2011 to 2021 were selected, and 269 papers were found within the research scope. The Prisma flow diagram was used for screening. In the second stage, Through the title and abstract review, 69 papers were removed. In the third stage, 58 more papers were removed through an entire paper review. The exclusion criteria used in stage 2 and 3 are on the slide. Finally, 52 papers were selected for the final analysis. For the descriptive analysis of our findings, out of these 52 papers, 27 discussed local air quality around specific airports. 17 papers examined regional air quality by assessing air quality at a few airports within a particular region, and 8 papers discussed global air quality, attempting to determine every airport. This map shows the geographic distribution of the research on either specific airports or regions. This map shows that this research area has been limited to only a few countries. IPCC categorizes the emission calculation methods into tiers. Tier 1 is purely based on fuel supplied. Tier 2 is based on the number of LTO cycles and fuel. Tier 1 and Tier 2 are basic methods with minimal required data. Tier 3 uses operational data of individual flights. Tier 3A is based on origin-destination pairs. Tier 3B uses sophisticated models. However, according to 52 papers reviewed, the ICAO advanced approach under Tier 3A is the most used method. Tier 1 and Tier 2 measure aggregate emissions of the LTO cycle. The table shows the key variables used in Tier 1 and Tier 2 to estimate emissions. Key references under Tier 1 and Tier 2 are also mentioned below the table. Tier 3 methods calculate emissions under different flight phases. Mode-specific emission factor, mode-specific fuel flow, and timing mode values are the key variables used in Tier 3A to calculate aircraft emissions. The emission factor and fuel flow values obtained from the ICAO Engine Emission Data Bank follow the international standard atmosphere. Tier 3B software uses the actual operational values of each aircraft, engine-specific aerodynamic performance data, and meteorological data to estimate aircraft emissions. Key findings: Tier 3 method can generate more accurate regional and global emission inventories, as those methods use airport-specific values. Tier 3 methods are more beneficial as they can generate emissions under different flight phases. Some researchers used Aviation Design Tool 2006 emission database. Even though the inventory is not up to date, it is used as capturing and maintaining aircraft data is expensive. Tier 3B methods generate the more accurate emission inventory compared to the other methods. For example, whereas Tier 3A method use average operational values of aircraft, Tier 3B method use actual operational values of each aircraft. Conclusions: By reviewing 52 papers, it is imperative that the aviation industry maintain accurate emission inventories to assess the local air quality impacts. Emissions directly emitted from aircraft capture the actual emissions when compared to measuring pollutant concentrations of the atmosphere. Emissions under different flight phases should be measured separately to identify the inefficiencies of those phases. When using the ICAO engine emission data bank values for emission factor and the fuel flow to estimate the emissions, those values should be adjusted considering actual atmospheric conditions. Next steps, we will extensively evaluate emission calculation methods to develop the most accurate model to estimate emissions around the airport. We will evaluate the influence of other airport sources on local air quality. We will use Brisbane Airport as a case study to apply our model. I believe we could help airlines and airports to improve the ambient air quality. Thank you all for listening to my presentation.